All right, AP Physics. This is the lesson that we worked on prior to the break and and yesterday on Monday, January the 8th. So I'm going to go ahead and just finish up on video, and you can finish up on video as well. Okay, so I'm going over some of the problems we've already done. I'm just going to do the whole thing. Okay, so a toy car in the figure above enters a vertical circular loop with an initial velocity and moves completely around the loop without friction. If the car has no means of self-propulsion, which of the following is true of the car's acceleration at point P? Okay, so its velocity at this point right here is going to be up here. That would be its tangential velocity in a straight line. It would be upward, so it is vertically upward. That's what this is, but that's not true of the acceleration. It's true of the velocity, that it's vertical upward. It is in the direction of the velocity, and that's not true. That's saying the same thing. It is directly towards the center of the circle. So that would be a centripetal acceleration looking like this, and that is correct. However, you got to be careful. It's not the best answer. It has components both downward, so it's going to have another component like this, and toward the center of the circle. That is okay. That is true. All right, it has components both downward and toward the center of the circle. That is the correct answer, is D. So gravity is pulling it downward, centripetal acceleration, gravitational acceleration that is, and centripetal acceleration towards the center of the circle. Okay, an artificial satellite orbits Earth at a speed of 7,800 meters per second and a height of 200 kilometers above the Earth's surface. The satellite experiences an acceleration of gravity due to... Alright, so I'm still a little puzzled where that comes from. It might be the tangential, I don't know, but it's not it. It's not it. So here's Earth. And here is the satellite going around like that, and it's saying that that's 200 kilometers above the Earth's surface. Okay, well, this is more of a concept question. On the Earth's surface, G equals 10 meters per second squared, but they're using the more precise value of 9.8. So the formula for G equals Newton's gravitational constant, 6.67 times 10 to the negative 11th, times the mass of the planet, which is the mass of the Earth in this case, over r squared, or d squared. R and d mean exactly the same thing, okay? So all you need to understand is on the Earth's surface, this is the gravitational acceleration, and it has a certain value of r. Okay, from the center of the Earth to the surface. If it's 200 kilometers above, then r is a little bit farther. It's from the center to this out here, to this bigger circle out here. If this number is bigger, then this number is going to get smaller. It's definitely not going to be zero. There is no zero gravitation when you're circling the Earth. And we'll talk about that at other times. We've mentioned it before. So the answer is it's less than 9.8 meters per second, but greater than zero. That would be the answer there. This one right here. Okay. Next, number 3. A meteoroid is in a circular orbit 600 meters above the surface of a distant planet. The planet has the same mass as the Earth, but has a radius that is 90% of that of Earth's radius of 6370. Okay, so if we do a quick calculation there, well, they're asking, first of all, the acceleration of the meteoroid due to the gravitational force would be. Okay, so we're just going to take that number 6370 times 90%, and that gives us 5733. Okay, now it is 600 kilometers above that, so we're going to add that 600 back onto that. And what we get is 63.33, which is essentially the same as the Earth's radius. So the r in both cases is going to be the same. So again, we're going to use this formula: G equals the gravitational acceleration of the planet. So in this case, the m could be either Earth or this other planet over r squared. All right, so we're going to say that the r's are effectively the same for both the Earth and this new planet. Okay, but it is saying that it has the same mass as the Earth. Okay, so that means m is the same as the Earth. R is effectively the same. That's such a minor difference. I mean, you got to go to 3 significant figures to see that difference right there. So we're going to say that both m and r are the same, and that means it's going to have the same gravitational acceleration. So that would be 10 meters per second squared toward the center of the planet. It would be that one right there. Okay. All right. So we've got this going around in a circle. It's being held on only by a friction force. The radius is going this way. The only force acting on this is the centripetal force, AC, right there. Okay. So it says during an experiment, an object is placed on a disk that rotates about an axle through its center, as shown in Figure 1. The block is a distance r 0.1 meters. You can write that down here. From the center, and rotates with a constant tangential speed of 60 meters per second. So again, you can just draw an arrow right there, 0.60 rather, meters per second. Okay, a free body diagram of the forces exerted on the block shown in Figure 2 above with an unknown friction force. Okay, so what is the force of friction exerted on the block? So in this case, the only force holding it inward, let's get here, the only force holding it inward is the friction force. Okay, so the friction force equals the centripetal force. That's the only force acting on this, because there's only one acceleration, and to have force you have to have acceleration. F equals ma. All right, so the centripetal force is going to equal the mass of the block. Okay, do we know what that is? Well, we do. We know that it has a weight of 2 newtons, and we know that weight equals mg. Remember, this is just a special case of F equals ma. Weight is a force, mass is mass, and g is gravitational acceleration. So if we solve that for m, we get m divide both sides by g equals weight over g, which equals 2 newtons right here, over 10 meters per second squared, which equals 0.2 kilograms. Right there, kg, I'm about off the page there. Anyway, that's the mass, okay? Okay, so the centripetal force equals mass times centripetal acceleration. What's the centripetal acceleration? Centripetal acceleration equals tangential velocity squared, this number here, over r, this number here. So we can put all that together to get the centripetal force, which is the friction force. So I'll write that equals friction force. It's the only force pulling this block inward. That equals mass, which we just said is 0.2, times velocity, 0.6, squared, don't forget to square it, over 0.1. So that means the friction force is going to equal times 0.2 divided by 0.1. It's going to equal 0.72. And it's a force, so it's in newtons. Okay, and that's this answer right here. Okay, so think about that. Do this, cover this up, and come over here and see if you can write it out a second time right there, okay? Without looking at it. You've got to practice these problems, not just watch them, practice them. See if you can do that by yourself. Okay, next one. Number 9 is this one. Okay, so it says a cart of mass M rolls past circular bottom of a hill, point P. Which of the following statements about the normal force Fn, so that's the one that's going this way, its weight is going down, exerted on the normal force exerted on the cart at point P. So what's the normal force right there? Okay, so let's look at the choices. Okay, so the cart at that point, sorry, it's not on the same page, so let's draw it right here. The cart is starting to get pushed upward, up this slope right here. Sorry, up this slope right here. It's starting to get pushed up that. So that means the normal force is going to have to be greater than the force of gravity. Now, it might appear that it's going to be the same because it's on a flat surface, but it's starting to be accelerated upward at this point. All right, so that means force normal is greater than mg. Again, that's just force of gravity or weight. It's greater than its weight because it's starting to get pushed up a ramp. Let's read the other options. Fn equals mg because normal force on an incline equal to mg cosine. That sounds like a good answer. It does, but it's actually being accelerated uphill at that point. Fn equals mg because the speed of the cart is neither increasing nor decreasing at point P. That's just not a true statement. This one looks like a reasonable answer. Fn is equal to the centripetal force on the cart because only the track can exert a force toward the center of the circle. Okay, that looks like not an unreasonable answer there either. Okay, but Fn is greater than mg at point P because the cart is experiencing an upward acceleration, and that is the correct answer. Another way to think of this problem is rather than it rolling down a hill and back up a hill, imagine that it was flat on this table and it was just doing what we usually think of circular motion. It's horizontal. Then the only force would be the centripetal force, this one right here. The centripetal force pulling it inward. Okay, so that force always has to be greater than any force pushing it out, otherwise it won't stay in a circle. So now what we've simply done is, let me change this arrow actually, we've added weight to it, mg. So if this force, the weight, were greater than the centripetal force holding it in, it would go flying off into space. It would go out this way. All right, so this has to be a greater force to hold it into the circle than the weight of it. Okay, let's go to the next problem. It's number 10. The figures show a cart moving over a hill, case 1, moving at the bottom of a dip, case 2, and moving at the top of a vertical loop, case 3. Let me get these on screen here like that. Okay. In each case, the normal force acting on the car, Fn, and the weight of the car is Fg. In which case is it always true that Fn is greater than Fg, and in which case is it always true that Fn is less than Fg? So let's look at A. Case 1. Okay, so it's saying that Fn is always greater than Fg. So Fn is the force pushing normal to it. Okay, and Fg is the gravity pushing it straight down towards the earth. Okay, well, if we imagine, just do a little thought experiment, we imagine this cart in case 1 is coming really fast. It could actually be going so fast it flies off the track. It's actually in the air. Okay, you may have seen that if a car goes over a hill too fast, it can actually, they say catch air. That means it flies in the air for a little bit and then it ends up coming back down. So if it did that, the car would be in the air right here. There would be no Fn. Fn would be 0 in this case. Okay, so the idea that Fn is always greater than Fg in case 1, this one or this one right here, is not true. So you can eliminate that one without even looking at the second choice. Okay, Fn is greater than Fg always. Okay, so the normal force is greater than the gravitational. We saw that on the last problem. That's true because it's accelerating upward. So Fn is going to be greater than Fg. That's true here. All right. In case 2, and in case 1, Fn is less than Fg. Well, let's go back to this example. Let's say it isn't going so fast that it's going to actually fly up into the air, but no matter how fast it's going, it's always going to lift a little bit off the ground, or try to lift a little. It may not lose contact with the ground, but when it gets here, it's going to slightly be elevated upward a little bit right here, even if it doesn't actually fly into the air. So as it goes over the top of this hill, Fn, even just slightly, is going to be less than Fg for a moment. So both of these are true. Those are both true. Now let's look at the others. You may say, well, wait, I see more than one that looks like it's true. Okay, so case 2, Fn is greater than Fg always. And case 3, Fn is less than Fg always. Not necessarily. This one should be Fn is greater than Fg always. Okay, so we said that already right here. Is Fn less than Fg always here? No, because if the force holding it to the track is less than the gravitational force, it's going to fall. It's going to fall. If this goes too slow, then the gravitational force is going to win, and it's going to cause that to fall. So this is not true. And finally, Fn is greater than Fg always in case 3. And again, the normal force is greater than the gravitational force always. Again, not necessarily. Okay, so Fn is less than Fg always in case 1. Okay, we said that was true up here. Okay, so that's true. But no, it's not always true. It depends on, case 3 depends on the speed of the cart. Okay, if it's fast, it sticks to the track. If it's not fast, it doesn't stick to the track and it falls. So that could be either way, Fn greater than or Fn not greater than Fg. So this one, this part of it is not true. So this is not true. So the answer is B to this one.